programming. We start the second semester with a very interesting talk. We have invited nice five guests. Diego Morán, he's a professor at Virginia Tech, most of you probably know him. And he's going to be talking about on the polyhedrality of the D branch and other closures.
Thank you, Rodrigo, for the invitation. I'm very happy to be here. So this talk is about some theoretical properties about cutting planes for mixed integer programs. And this is joint work with Sanjeev Dash and Octane Guluk from IBM Research. Okay, so let me tell you a little bit about how this started. So I was a summer intern at IBM during summer 2012, so May to August, something like that. And we start working in this kind of properties. Okay. So Marcus is not here, but Marcus was actually one of the first summer intern that worked with Sanjeev and Octane. Sanjeev and Octane. So I think I was the second Chilean working with them. So during that summer, during those 3 months, we were able to prove this result that I call T branch for the case when T is equal to 2. So that was the only thing that we were able to do at that time. And finally, 3 years later, we are happy, as you can see up there. We were able to generalize this result for any T greater or equal than 2, and actually greater or equal than 1. Okay. And actually, we also study a similar object, and we also prove the same result for this other object. But in this talk, I will focus on this result. That is, I mean, it's fairly new. I mean, we finished this a couple of months ago, and we're still writing the paper. So let me start with some notation. So if you don't know what are cutting planes for IP, so you want to solve this problem, all the interpoints inside this polyhedron, I mean, just linear inequalities. So this problem is very difficult. So what you do is you approximate these interpoints by the LP. So you only consider the linear inequalities. And in general, this approximation is very bad. So when you solve this problem, it will not be integral solution. So what you do, you start adding more inequalities. And when you do that, this approximation becomes better. So at the end, the hope is that you obtain this very good approximation that we call the integral hull. So this is how we use cutting planes in integer programming. So I will not tell you about how we use these cutting planes, but I will tell you about some properties about these cutting planes. So a question is how you compute, how you define these cutting planes. One way of doing it is by using split sets. What is a split set? You can remind these are two parallel hyperplanes, okay, that doesn't contain any integer point in the interior. So these vectors are integral. So in a picture, what you have, this is a split set. So it's a parallel hyperplanes that doesn't contain any integer point in the interior. So this is a split set for us. And how do you use these sets in order to compute cutting planes? Let me show you what you do. So you say that valid inequality is a split cut if it's valid for this set P, the original polyhedron, when you remove the split set from it. So this is a split cut. So how this looks in a picture, you have your polyhedron P, you are interested in the integer points inside P. This is maybe a bad approximation. So what you do is you consider any split set, you remove it. When you remove it, you are not removing any integer point because it doesn't contain any integer point interior. And then you start computing some cutting planes. So valid inequalities for this P minus S. And the hope is that this region is easier to understand that understanding the integer points. That's why we use this kind of split sets. So you compute these cutting planes, and what you obtain is a better approximation. And this very simple geometric procedure actually is very important and very useful in practice. So these cutting planes, these split cuts, have very nice properties. most solvers use a class of cutting planes that are based in split cuts. And also these split cuts have very nice theoretical properties. I will study a property that is similar for our case. Okay, so let me tell you about some generalizations of split cuts. So the first generalization is to, instead of removing one split from P, to remove two. Okay, so we call this kind of cuts cross cuts, because when you take two splits at the same time, this looks like a cross. So the hope is that if you take two, you obtain a better approximation, because this cutting plane will be stronger in general than when you just remove just one split. So this is cross cuts. Further generalization, instead of removing just two, you use fix a number t and remove t splits. And we call this t-branch split cuts. And for t equals to 1, these are split sets, t equals to 2, cross sets. So we will study this kind of cutting planes in this talk. So what is the property that we will study? This is a very nice property that split. We knew that was true for splits. And the property is as follows. Consider the object when you intersect P with all possible split cuts. Since you have infinite many split sets, these all split cuts are infinite many cuts. So infinite many valid inequalities. So this object may not be a polyhedron. It could be any convex set. But what was proven in 1990 is that this object that could be very strange, in fact, it's not strange, is also a polyhedron. This means that you only need to, in order to obtain this object, you only need to intersect P with finite many split cuts. Yes?
I don't think you need from the figures that the split cuts are always like defined by lines, right? So
yeah, by hyperplanes, yes.
So we lose convexity because it becomes like a disconnect set.
No, because what you do is you take all the valid inequalities. Okay? So let me. So what you obtain when intersect with P is a convex set, right? Mm-hmm.
What could cause the loss of polyhedrality? What potentially cause?
Because you have infinite many possible split sets. Yes, because you could consider any possible split set. So you have infinite many split cuts. So you, at the end, you are intersecting with infinite many cuts. Yeah, but good question. Thank you. So this result is not trivial because you have infinite many split cuts in general. So this was proven in 1990, and later on, many other people work in the same result, but using different approaches that are very, interesting by their own. Okay, so this is the result that we want to prove for the more general case, the T-branch split cuts. Okay, so we define what is the, instead of the split closure, we define the T-branch split closure, and it's nothing more than intersecting P with all T-branch split cuts. Given the T, we intersect all possible T-branch. Remember, this T-branch is the cuts that would take when removing from P T split sets at the same time. So we'll prove that this object, that is, it could also be weird because you have infinitely many T-branch split sets. This is also a polyhedral set. So this is what we will do in this talk. Question? No? Sorry. Because you remove two split sets at the same time, so the cuts that you are obtaining are different.
So when you say the first result, you say all the split cuts are one
just from one split, yeah, just one split. Here you take two or T at the same time. Thank you. So what is the rest of the talk? First, I will show you how you prove that this split closure is polyhedral. So this was the known result. And actually, we'll show you two proof techniques. The original one, given by Cook, Cannon, and Skyver in 1990, and a second proof that is very interesting, that was given by Anderson, Kornejos, and Lee, and also was generalized by Gennady Averkov. And why I'm showing you these two techniques, because we will combine these two, in some sense, we'll combine these two techniques in order to prove the more general result. And at the end, if we have time, I will show you other closures that are defined and that you can also prove that they are polyhedral. Okay, but the focus of the talk will be the first two parts. Okay, so let's start with polyhedrality of split closures. So how you prove that you only need finite many cuts, not the infinite many. So the first thing that you notice is that given one split that you remove, you can consider infinite many cuts, right? But not all of them are important, because some of them are redundant. Okay, so the cuts that you will actually consider will be the ones given that gives you the convex hull. So these finite many cuts. So given one split, are finite many are interesting. So this set is a polyhedron. Okay, so that's the first idea. Second idea is that given this intersecting P with all possible split cuts is the same as considering intersection for all possible splits of this convexification. So you are considering here only the important split cuts. So this is the first idea. Second idea is that given that you have this is a polyhedron, then if you find, for some magical reason, that is a finite set of splits that actually give you the split closure, so instead of infinite intersection, you have this finite intersection, since these all sets are polyhedra, then you will prove that the split closure is also a polyhedron, because this set is a polyhedron. So our goal in these proof techniques will be to find this finite set of splits that will give you the split closure. So this is the goal for the proof techniques. So let's study the first proof techniques, the original one, that I call geometric and by induction proof technique. So in order to understand this proof technique, with this geometric result, and it's as follows. If you have a ball of a fixed radius, and this ball is covered by a union of splits, for instance, it's like this in the picture, this implies that at least one of the splits must be fat enough in order to cover the ball. And fat enough means that, in some sense, that the radius, the distance between the hyperplanes is enough to cover the ball. That means fat. And actually, you can prove that given a radius, there are only finite many splits sets that contain the ball. Because if the split is fat, what I wanted to say is that there are finite many fat splits. You will have infinite many thin split sets, because if you enlarge the number, these kind of sets become thinner. But if it's fat, there are only finite many possibilities. So this is important. So if the ball is covered by the splits, at least one is fat, and are finite many split and fat split sets. So this is one result we will use, and the proof is as follows. So you have your polyhedron P, and you want to prove that the split closure is finite. It's a polyhedron. So we use induction first. So instead of induction in dimension of the polyhedron. So this polyhedron had dimension 2. So we look at the facet that has dimension 1. So what we can prove there is that by induction hypothesis, you prove that the split closure of each facet is given by a finite intersection. So for each facet Fi, the split closure of the facet is given by this finite set of splits. So for every facet, the set may be different, but we don't care about that. So by induction, we know how to compute the split closure on each facet, not in the polyhedron, but on each facet. So, but we will use these split sets in order to approximate the split closure of the original polyhedron. So what we do is, instead of considering the infinite intersection, we consider the intersection of these finite many splits, the ones given by the facet. So this yellow set is this approximation. And this approximation is equal to a split closure of P on the facets, because these split sets are coming from the induction hypothesis on the facets, but may not be equal to a split closure because this is finite intersection and this is infinite intersection. So it may not be equal. So what will happen is that you may need to cut, in order to obtain the split closure, this yellow set is bigger than the split closure, you may need to cut some points in the interior of the set. Because in the facet is equal, so you don't cut anything there, but you may need to cut something in the interior. And what you can prove is that there are some space here, and that space you can put a ball, so of fixed radius, that only depends on the polyhedron. And these balls, in order to obtain a split closure, you want to cut those balls. So at the end is that the splits that you need to add to this intersection are ones that are fat. Because the ones that are too thin, they will not cut anything in the interior, and you know that there is no split set that will cut more on the facets. So in order to obtain the split closure, you only need to add fat split sets. So at the end, this is what you obtain. The split closure, this infinite intersection, is given by the approximation, given by the split sets that give the split closure on the facets, plus the intersection of all fat splits. This is finite, because, I mean, by induction was finite, and these fat split sets are also finite now, finite many. So this is a polyhedron. So we don't need the infinite many. And as a conclusion, what you can say is that if the split set is too thin, then it will be dominated by the approximation. And if this fat is dominated by itself. So that's why you don't need all possible split sets. Okay, so that's the first proof. Let me show you a second approach. It's quite different and some sense better. So for this approach, we need this result. So this result is saying that if you consider any subset of non-negative integers, then there exists a finite set, including in the original set, so that any other point in the set is dominated by one on this finite set. Dominated in the sense that they are minimal elements. Okay, so this is a very useful result. It's called Gordan-Dickson lemma. So this set X will be infinite, but you know that you will find a finite set that will dominate every other. Because any point X is dominated by at least one. So we'll use this result. So let's see. In order to use this result, we need to relate splits with non-negative integers. So this is what we will do. So remember how you compute a split set, split cuts. You remove from P a split, you compute the cut, and what you obtain is this object. This is the convex hull. And you can notice that this convex hull is defined by these 2 points. And these 2 points are defined by the intersection of the vertex with the hyperplanes defining the split set. And this is the only thing that defines what is the cuts given by the splits, right? So it doesn't matter what split set you consider, but these intersection points define the convex hull of P minus S. So we're interested in these points. Okay? So these are called intersection points. And these intersection points are not anything. They have very nice properties. So what you can prove, we didn't prove it, but it was proven before by Cornelius, Anderson, and Lee, is that, first of all, if B is a vertex, like this one, and R is an array, the intersection points are not too farther away on the array. This is like a bound. So this is a bound so that there's no intersection point after this bound. So it's bounded in some sense. And also it's discrete in some sense. In the sense that there may be infinite many intersection points, but if you consider any bounded interval, there are only finite many here. There could be infinite many that are approaching to the vertex, but that doesn't matter if you consider a bounded set, you will be able to count them. They will be finite. And these two properties, what they allow us to do is, in fact, that you can actually enumerate these intersection points. Given the vertex and array, since they are bounded, and there are finitely many on every bounded interval, then you can enumerate these intersection points. So we do that for every array. And actually, what will happen is that for every split, you will assign the intersection points corresponding to the split. And these intersection points have a number because we enumerate them. So at the end, what will happen is that if we have two split sets, for instance, we compute the intersection points, we associate the number, for instance, 1, 2, and 3, 1. And we'll notice that if the split sets can be compared, I mean, the cuts can be compared in terms of these numbers. So we don't need to look at the convex hull, but we can look at the numbers. For instance, in this case, we cannot compare these numbers. No vector is less or equal than the other. And you can see that the cuts that we obtain are also incomparable, right? Because we have this cut and this cut, again, by 1, 2, and 3, 1. But it could be the case that we can compare them. So for instance, this split set, the purple split set, gives a worse cut because this cut is implied by this cut. Okay, so this split set, the fattest one, the fatter one, gives a better cut, and you can notice that this fattest split set has a better number, it's a minimal number in some sense, because this number is less or equal than the vector given by the other split. So what you conclude at the end is that you can compare splits. So this split gives better cuts than this one, because this is contained here. All cuts here are implied by cuts here. This happens if and only if the numbers are also comparable. And now you have non-negative numbers, right? Integer vectors. And you can think that if I can find a set of minimal elements here, you will find a set of minimal splits. And by Gordan-Dickson lemma, this is a finite set of minimal elements on the integral vectors, but that will give you a finite minimal set of splits as well, because these are related. Numbers are related to splits. So what you obtain at the end, by using Gordan-Dickson lemma, is that you have a finite set of non-redundant splits, the ones that are giving me the best cuts. And this was proved first by Gennady Averkov. So what you can say at the end is that the split closure, this infinite intersection, can be written as intersection of these non-redundant splits that are given by Gordan-Dickson lemma. And this is a finite set because Gordan-Dickson lemma gives you a finite set. Okay? So every split set will be dominated by 1 on this Gordan-Dickson lemma. Remember Gordan-Dickson lemma, every element on the set is dominated by 1 in this finite set. So you can say the same for the splits. So these are the two proof techniques. So some remarks about these proof techniques is that the original one, as I showed to you, only shows the polyhedrality result. But the second proof is more powerful in the sense that, as I showed to you, allow us to prove two more things besides polyhedrality. The first thing is that actually you find a finite set of minimal splits, in the sense that for any other split, you can find a split S coming from a finite set of splits that dominates the original split. So this you can take from an infinite set, but you can always find a split S from a finite set that dominates this one. So this is a very, we didn't know that before using this technique. The original proof doesn't tell you this. Okay? And the second thing is that this Gordan-Dickson lemma technique can be adapted. Instead of intersecting all possible splits, you intersect an arbitrary set of splits. So you can also prove this very easily by using the same technique. Because Gordan-Dickson lemma, you use any set for Gordan-Dickson lemma. Okay. I will say exists, just existence. I don't know how to construct them. What? The second one, I don't remember if the Gordan-Dickson lemma proof gives you constructiveness. That's the thing. I don't remember. So what we prove now, finally, is coming our result in slide 54. We prove the same result. Actually, not just polyhedrality, but we prove that for the T branch now, not the splits are one branch. Prove that for T branch, there is always a finite minimal set of T branch splits that dominate any other T branch splits. And in particular, this proves that set is a polyhedron because you only need finite many in the intersection. You say that there is a lot of proof of previous results. You're the split set result. Why did so that people reprove that there are some new ideas that are more than these two ideas? Yeah, for instance, I mean, the two proofs I show you are, in some sense, are different. Right? Because some use geometry, you need to cut a ball in the far split, and the other one you use this kind of Gordan-Dickson lemma result that gives you these two additional things that you can say, for instance. Yeah, a lot of proofs. Juan Pablo was there. Yeah. Yes, for instance, Juan Pablo says that his proof was the first constructed proof for the split closure, for instance. But also Cook also said that his proof was also constructed because it was by induction. So you can start with the dimension 1 and go to dimension 2, etc. But I haven't read those proofs his proofs in detail because we only need these two techniques. Okay, so we prove the same result for T-branch splits. So let's see what let me remind you what was T-branch splits, because probably you forgot. So T-branch, you fix a T, and you remove from P T split sets at the same time. And you compute cuts based on this object. Okay, and split sets were one branch. And so this was proven before. We, during the first summer at the internship, we proved this for two branches, but we were not able to prove the general result that we just proved a couple of months ago. So what we want to prove is the following. This, it may look scary, but what it's saying is that given any set of T branch splits, there is a finite subset of T branch splits that dominates any other. So it's the same as the split case, but for T branch splits, right? And this in particular implies the polyhedrality of the intersection of all of them, because since all of them are dominated by one of these, this intersection, infinite intersection, can be written in terms of these T branch splits only. So we'll prove this result. So it's the same, more powerful result. So any T branch split is dominated by one coming from a finite set. And actually, I will not show you the general result, but I will show you the case for crosses, because the proof is very similar. It's the same actually. As you can think as the crosses that I will talk about now are the T branch splits, and the splits that are one branch splits are the T minus one branch splits. But the proof technique will be exactly the same. Because we will use an induction in T. So if I show you a case from 1 to 2, then you will figure out T minus 1 to T. So what we want to prove in this case, again, for T equals to 2, we want, for every arbitrary set of crosses, we want to find a set of minimal elements that is finite that dominate any other cross. That's what we want to prove. We want to prove that every cross can be dominated in this sense by a cross from this finite set. And this will imply that this two-branch closure is a polyhedral set. Okay? Because any other cross is dominated by one from a finite set. So why we cannot use the original proof to prove this crosscut case? Because of the following. Because before, when we have fat splits that cover a ball, I told you that you can prove that that implies that these are finitely many splits. But when you consider fat crosses, this could happen. So a fat cross could be given by one fat split and one thin split. And the problem is that these are not finitely many crosses because these thin splits could be infinitely many. So there are not finitely many fat crosses. Before we had finitely many splits, here fat splits, but here we don't have finitely many fat crosses. So this is one problem. We cannot use the original geometric proof. The second difficulty is that we cannot use the intersection points technique because now we first remove one split, and when we remove the second split, the convex hull is given by these many intersection points. This one, this one, this one, and this one. With these two, we're okay because are given by the rays. But these two other intersection points are given by the first split. And you will have infinitely many first splits because you are considering all the crosses. So we will not have finitely many rays. We cannot associate an integral vector as in the previous case, so we cannot use Gordan-Dickson directly. So we cannot use the second proof as well. So what we will have to do is somehow, instead of working with Gordan-Dickson lemma, we study a generalization. Instead of less or equal inequality in terms of vector, comparative vectors, we find another partial order. And we will need some properties of these partial order sets. And then we can write the result in terms of this new terminology. And when we do that, we do very similar things to the first two proof techniques. We use induction, we find a finite set of minimal elements, etc. But we first need to understand this more general result. I mean, general terminology. So let's write the result in terms of this partial order business. So the first thing is that given two crosses, we'll say that one cross is greater or equal than the other if and only if this convex hull contains the other convex hull, meaning that this C prime cross C prime is better if and only if it gives you better cuts. So this is the order we'll have here that you can define for crosses or for any other T-branch split set. So this will be the order. So we will be interested to find the better crosses, means that we want to find the minimal crosses for this order. And this order is given by the polyhedron P, as we can observe here. Given P, we want to build polyhedrality for that P, we define this partial order. So we want to find a finite set of minimal elements. So given this is quasi-order, it doesn't have antisymmetry. So they could be related, but not necessarily equal. So this is the partial order we use. Now we need some properties of these partial orders in order to stay or result in this terminology. The first is dominated subset. So we say that D is a dominated subset for X if every X in X is dominated by one D in the dominating set D. So this set not need to be finite, but it will be dominated set if it dominates any other. This D is subset of the original one. Okay? And furthermore, we will say that the order, given a set with that order, is fairly well ordered. Every subset has a finite dominated subset. Okay? For instance, CP, I mean, non-negative integral vectors with the usual order is fairly well ordered by Gordan-Dickson lemma. Remember, any subset of non-negative integral vectors have a finite dominated subset by Gordan-Dickson lemma. So this says this definition is a generalization of Gordan-Dickson lemma in some sense. So given these two definitions, our result is stated as follows. For every set of crosses, we want to find a finite set of dominating crosses that dominate any other. In other words, we want to show that this order is finitely well ordered. So every arbitrary set has a finite dominating subset. So this is what we want to show. Okay, in this partial order set terminology. So now we need some properties of these orders that are not necessarily the ones that the usual inequality has. So the first property, I mean, we will not use this lemma, but we will use two corollaries. But this lemma is saying the following. If you have P different partial order sets, so different sets with different orders, if you consider the Cartesian product of these sets, given with the partial order defined component by component, if the original sets were finitely well ordered, meaning that they satisfy this Gordan-Dickson lemma kind of property, then this Cartesian product is also finitely well ordered. So it's always a finite dominating subset. So why we need this lemma? Because we need these two corollaries that we'll use later. The first corollary is saying that if you have the same ground set, X star, but different orders, then by using the lemma, you can prove that actually there is a finite set, X sub f, such that any element of the original set is dominated in all the inequalities at the same time by this element from the finite set. So I call this property simultaneously dominating subset because it's dominating at the same time for every order. Okay, that's simultaneously. This is the first property we'll need later. Second property is that I call finite dominating subset for the union. And here the context is as follows. Let's this be the collection of all split sets. Remember the T minus one branch splits. You can think of them as the T minus one branch splits. If you have a collection of polyhedra, a finite collection, then by the Gordan-Dickson proof technique that I showed you before, we know that these sets, every of them, for every polyhedron, you find a finite set of split sets that dominate every other. That means that these are finitely well ordered posets. Because for the second proof technique that uses Gordan-Dickson lemma, this result that we want to prove is true. But the thing is that if this is true for this polyhedra, P polyhedra, then you can also say that if you consider the split sets, with this order given by the union of these sets instead of every Q, this set is also a finitely well ordered. So given this partial order, you will also find finite set of dominating elements, finitely well ordered. So where is this coming from? Also from the lemma, this Cartesian product thing. And the thing that if you want to notice, you have these orders, and this order that is given by the union can be written in terms of the order given by every polyhedra Qi. But the proof is not important. The thing is that given that you have finite dominating subset for every polyhedra, you can find a finite dominating subset for the union. That's the thing that we need to remember for later. So this finite dominating subset for the union. Okay, now the proof. Okay, so we want to show that this poset is finitely well ordered. So every arbitrary set has a finite dominating subset. And this we want to do with the order related to the polyhedron P. So what we do, we use induction. So we consider the facet as before. And by induction, we say that all of these orders are finitely well ordered. So for every facet, this has a finite dominating subset. So now we have the same set C with different orders. So by applying this simultaneously dominating subset corollary, we can prove that given these orders, this is a finite set, so that every other cross is dominated by one of these crosses from the finite set on every facet at the same time. So every C is dominated by DCI for all facets simultaneously. Okay? And this is important because this cross dominates all of them, meaning all the facets. Okay? So why we need this set of crosses? Because now we can partition the arbitrary set of crosses in terms of which crosses are dominated by which CI. So this is a partition because all of them are dominated by another partition, but this is the union is C because any arbitrary cross will be dominated by at least one in all the facets at the same time. So now, if we want to find a dominating subset for C, we can do it by finding a dominating subset for each CI. And since these are finite many, then we'll find a finite set of dominating crosses at the end. So now for each CI, now we'll approximate the cross closure not by the finite infinite intersection of these sets, but just by one of them. The one given by the cross dominating in this set CI. So each cross here is dominated by this CI. So I dominated by this one. So this is approximation now. And now, since any cross in CI is dominated on all the facets at the same time by this one, any cross here will not be able to improve this approximation on the facets. But it could improve it on the interior, as before, as in the original geometric proof for the split closure. So if you have a cross that is too thin, you know that it doesn't dominate CI in the facets, and since it's too thin, it will not dominate anything on the interior. So what you can conclude is that by geometric argument is that the crosses that are too thin will be dominated by CI because they are dominated on the facets and they will not cut anything from the interior. Remember, this yellow set is now given by CI. So these two thin crosses that both of the splits are thin will not improve this approximation. So they are dominated by CI. Okay? So now the only crosses that we need to dominate are the ones that are fat. And fat means that at least one split is fat, as we saw before in the picture. So now give it a cross here that is fat. So it has a fat split and an arbitrary split that could be thin. And the important thing here is that the fat split sets are in some sense finite. So this is good, finite. This may be infinite because it could be considered thin splits. So how we dominate these ones? So we'll dominate this kind of crosses given by fat split and arbitrary split as follows. If we want to dominate this cross by other cross, we'll try by dominating this one by a cross that maintains the same fat split. So if we do this, this domination by definition is convexial of P minus the union, and you can do some algebra to write this domination in terms of crosses as domination of splits in terms of this, not P, but P minus this fat cross. Sorry, fat split. Okay? So if any split here can be dominated by a finite set of S-prime splits, then we'll be done. So how we do this? What you can notice is that what is P minus one split? If you remember the pictures, if you remove from P one split, you obtain a union of sets. Okay, so this order is given by a union. So then we can use the second corollary, the one that says that if I dominate for two sets, I dominate for the union 2, we can say that any cross of this form will be dominated by one of this form, where S will come from a finite dominating subset of splits. Because we have this corollary that works for the union too. Okay, so finally, summary is that how you dominate the crosses. Well, any cross in this arbitrary set belongs to one Ci. Now, if this cross is too thin, it will be dominated by the corresponding cross Ci, that comes from a finite set. Otherwise, it's a fat cross. So this form, this part is finite, and we find a dominating subset of crosses of this form that dominate this cross. And this also comes from a finite set. So, summary, every cross is dominated by either Ci or a cross of this form that comes from a finite set, because fattest splits are finite, and this prime was proven to be finite by the dominating subset for the union, corollary. So this is how you dominate all crosses. And every cross is dominated by just one. That's the important thing. Okay, so this is the result. So we need to use these poset techniques in order to prove for the 2 branch in this case, or for the T branch. And the proof for the general case is the same. So what we can say about polyhedrality of other closures, let me define you. I mean, this is just a couple of slides. Let me tell you what are other closures, how you find cutting planes using other techniques. So remember that we start finding split cuts by finding valid inequalities for P minus 1 split, but you will do the same for every set that doesn't contain any integral point. So if you remove from P this set that doesn't contain any integral point, then you will not remove any integral point, right? So what are these lattice-free sets? You have the splits that in the interior doesn't have an integral point, so you remove from P to obtain a valid relaxation, or you can consider any other kind of lattice-free sets. This doesn't have any integral point in the interior. So what you do is, in order to compute, for instance, quadrilateral cuts, you remove from P this quadrilateral, and you compute the cut. So this may give you better cuts than the split cuts. But I mean, the trade-off is that split sets are very easy in some, because they're defined by just 2 parallel hyperplanes, and these quadrilaterals may be more difficult. But they are also useful. I also already defined what was a crosscut, so P minus 2 split at the same time. This is just to remind you, because instead of crosscuts, Sanjeev, Oktay, and my advisor from Georgia Tech, Shantanu Dey, they define what is called crooked crosses. So instead of consider this cross, you consider this crooked cross. That is actually given by 3 splits. This split, this split, and this split. But you don't consider 2 extremes. So this, I mean, why you do this, and why complicated? Because these cuts are stronger than the ones given by these crosses, and you need stronger cuts in order to solve your IP. T branch splits, already you know what this union of splits. And as another generalization is, instead of removing from P some splits, you intersect P with a lattice, and this lattice contains your integral points. Why this is useful? Because this lattice is an n-dimensional lattice, so it's very difficult. And this could be I don't know, a 2-dimensional lattice, for instance. That this problem will be easier than P enter the integral points, for instance. And actually, if this is 1-dimensional, this is related to split sets. And if this is 2-dimensional, it's related to crooked cross sets. So this is what I am telling you. So instead of removing a split, you intersect P with this lattice, and the lattice here will be given by the intersection of these hyperplanes. So you consider these hyperplanes and these other parallel hyperplanes. You obtain this lattice that may not be equal to the integral points, and you consider cutting planes for this object that are valid for the integral points, lattice points that are in P, valid for this set. So why this is useful, as I told you, actually this split closure, the convex intersection of all possible convex hull of P minus split, is equal to the intersection of all x, so that P transpose x belongs to integral points. So This was a very nice picture. Yeah, well, I don't have. Yeah. Because just one, I will do it very quickly. So you have your P. Yeah, but this is P, and before you were considered valid inequalities for this. So you remove a split set from P, right? And this is the split closure. And now you're intersecting P with all points so that this hyperplane has integral height in some sense. So you consider these hyperplanes. So this is P transpose X equals to some K integral. And you consider all possible integers. You intersect that with P, and then you are computing cutting planes for this object. Something like this. I mean, picture is not very good. No, it's almost good. Something like this. So you consider cutting planes for that thing. Instead of just one split, you intersect with the hyperplanes. They prove that. So this is why these are interesting objects. And also Shantanu, Sanjeev, and Oktay also proved that the crooked cross closure, the one that has the strange cross, is equal to, instead of intersecting with just one hyperplane, you intersect with two simultaneously. So this also is a lattice closure. Okay. So that's why that's also important. Polarity results, I tell you again, split closure was proven by a lot of people. Let me just tell you a little bit of history. The original proof just proved polyhedrality. Secondly, I mean, like 15 years later, Anderson, Collins, and Lee, they proved that it's true also for arbitrary set of splits. Later, there are different proofs that some of them gives you bounds on the size of the vector defining the splits, and different things. And later, Anderson, Lobo, Quentin Lobo, and Robert Weissmantel, they generalized this split closure result for an arbitrary set of splits, not for splits, but for different lattice free sets, similar to splits. And the strongest result regarding split closure is the one given by Abercoff. They use Gordan-Dickson lemma, and this gives you not only arbitrary set of splits, but also you find a finite minimal set of splits, dominating splits. Regarding polarity, these lattice free closures, these guys, Amitabh Basu, Robert Hilder, and Matthias Koppe, they proved that the quadrilateral. This is an old version of my slides. I don't know what happened. That it should be triangle closure. Instead of removing quadrilaterals, you remove triangles that are lattice free, like these ones. They prove by a super different proof technique. I mean, very involved proof technique, much more difficult than the one I show you. They prove that triangle closure also is a polyhedral set. So you don't need infinite many, you need finite many cuts. And we prove by using, actually as a corollary of the cross set result, you can prove that the quadrilateral closure, you remove quadrilaterals, this is also a polyhedral set. What else you have? This result I mentioned before, this generalization of splits. Instead of splits, you consider max facet width bounded lattice free sets. They prove that it's polyhedral. They prove that these integral lattice free polyhedra are also, this closure is also polyhedral. This polyhedral, this lattice free set have integral vertices. We prove the two branches split closure crosses just for an arbitrary set of splits. The first time, the first internship, we only proved this result, arbitrary set of crosses. It took a while to write the paper. And later, just now we proved that the branch, the more general result, you have a finite minimal set of dominating elements. And we also proved the same result, not only for the deep branch, but also for these lattice closures that I mentioned to you. And this is the result for the k-dimensional lattice closures. I mean, if you consider any lattice, arbitrary set of lattices, there is a finite set of dominating lattices that give you the closure given by these lattices. Okay, I mean, it's the same kind of result, but for these objects. Lattices of lower dimension, hopefully, than the integral lattice, but are a relaxation of this integral lattice is the one that we want to study. And this is all. Any questions? Time is here.